Okay, so whenever you go outside and you walk down the sidewalk or you walk by a building and you see the concrete that is there, do you imagine that the industry of manufacturing that concrete is responsible for 8% of all carbon dioxide emissions into the atmosphere from human-made sources, anthropogenic sources? And you can imagine, like, why would that be? Well, how is that? How is that possible? It's concrete, it's rock, isn't that stuff just mined out of the ground? How in the world is that contributing so much greenhouse gas to the atmosphere? Where is it all coming from? And this is something that I think is really, really hidden from view from everyday people. Concrete is absolutely a ubiquitous material, and we all encounter it every single day. It's literally the foundation of pretty much everything, from houses to large buildings to bridges to dams to sidewalks, all sorts of structures. Concrete is used to make all that. And we don't ever get to see where concrete comes from. Okay, so what is concrete? What's in it? Water. You know, when you buy the concrete from the store, the bags, and you want to make your patio or your sidewalk at your house, you add water to that. So there's water involved. There's sand. There's what we call aggregate, which is basically just like pebbles, small rocks that just bulk up the material and make it higher volume to fill our forms with when we pour our concrete. And then there is the magic ingredient. And to most of us, this is literally like magic. Cement. What is cement? A lot of times whenever we use the word concrete, some people use the word cement. Oh, it's a cement sidewalk. It's a cement wall. It's a cement bridge. Cement. Obviously, cement is only one of the ingredients in making concrete. Whenever we make, a lot of us know how beer is made. Beer is water, barley, and hops. So this is like our hops, our water, our barley, which is the bulk of the beer, and then we got yeast. Yeast is to beer as cement is to concrete. It's the magic stuff that makes it happen. And yeast is obviously a living organism. And cement isn't really alive in the biological sense, but it is very much alive in the chemical sense of things. Cement is an extremely active chemical substance. And where does cement come from? Okay, so you're mining sand out of the ground, you're digging it up somewhere, you're getting aggregate, you're basically quarrying stone and you're breaking it up. Water, obviously, we get water from wherever, it's all over the place. But what about cement? Is there a cement mine someplace? Some places there are. So back in the Roman times when they made concrete, they used volcanic ash as cement. So, volcanic ash. What's so special about that? Volcanic. Volcanic implies heat. So that ash, that fine particulate matter that comes out of a volcanic eruption, was at one point in the recent past very, 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 very hot. Heated material. And heat is the magic of cement. So, how is it that cement production generates 8% of all global greenhouse gas emissions? Well, it's because to make cement, you need heat. And lots and lots and lots of heat. So much heat that cement manufacturing is among the world's most energy intensive industries. if not the most energy intensive industry on a pound weight per unit of product basis. So how do we make cement? How do we get the heat to make cement? And what do we use? How do we take the heat and how do we get cement out of that? All right. Concrete that we use nowadays, there's all kinds of different types of concrete, and there's all kinds of different cements too. There's the volcanic ash-based cement like the Romans used. There's the lime-based cement, which is slightly different. But the cement that we use for the bulk of modern concrete is called Portland cement. Portland, I don't know the history of the term Portland, but it probably has to do with someplace in England where the stuff was first made or something like that. I don't know. But it's called Portland cement. And Portland cement is made up of what are called calcium silicates. So the element calcium silicate. Calcium, silicon, and oxygen. Now, this material is obviously, it's not naturally occurring in the proper form that you need to make a hardening cement. So cement is really nothing more than an adhesive. It glues the sand and the aggregate together, and the water basically combines with these things to make it hard, to make it turn from a powdery kind of stuff into a accretion mass that encapsulates all of the components of concrete and effectively makes artificial rock. And that's all that concrete is it's an artificial rock. It's a man-made rock. It's made using the same sort of natural processes that make real rock. It's just the human beings have taken that and controlled it a lot more. We can make the properties of the concrete fit our needs. And this Portland cement is key ingredient to make that happen. So calcium silicate. So obviously you need a source of calcium, you need a source of silicon, and then oxygen. So where do we get calcium? Well, we get it from limestone, right? Calcium carbonate, CaCO3. Where do we get silicon? We get that from sand, silicon dioxide, SiO2. And obviously there's oxygens on these already, but we can also get oxygen from the atmosphere, O2, from the air, right? Now, all these materials, this and this, can be obtained from the ground. You can go to the sand quarry and get your sand. You go to the limestone quarry and get your limestone. And now you have to convert that into cement. And where does that happen? The cement plant, right? Cement plants are they're all over the place. The closest one to me here is down near Allentown, here in Pennsylvania, in the Lehigh Valley. There is a couple cement plants down there, but they are spread all over the world. China has a very, very large amount of cement plants because China needs a lot of concrete when you got to build stuff for 1.5 billion people. And they're making Portland cement there. So these chemicals, calcium carbonate, silicon dioxide, these are very recalcitrant compounds. It's very difficult to get the silicon dioxide to kind of come apart, right? You can't just easily break this silicon atom off of the silicon dioxide. It doesn't come off very easily. Then the same thing goes for the carbonate and the oxygens that are on the calcium. They don't want to come apart. This is a very strong, these are very strong chemical bonds between the oxygens and the calciums and the silicon. So a cement kiln, a cement plant, its job is to basically heat the bejesus out of these substances to make them change form and form things like this, like these calcium silicate substances that can then be combined with water, and then the water will hydrate this and form new crystalline structures that will cause adhesion of your concrete and make your concrete hard. You'll make it from a slurry into a hardened, rock. Right? So, cement plant uses a cement kiln to do this. Cement kiln, a kiln. Obviously, most of us associate that word with pottery. Like this. Ceramics. You know, whenever we took art class in middle school and we had to make the cheesy little clay pots, and after we got our pot made from the soft, pliable clay, we gave it to the art teacher and they loaded it into a kiln. Our school, where I went, had electrically fired kilns. They were basically like a big chest freezer, and you open the lid and you put your clay, your ashtray or your mug or your clay coil pot on the refractory floor of the kiln. The door got shut, turn the knob, and next day you come back and you walk into the room and you stand by the kiln, and the heat that's radiating off of that kiln is absolutely mesmerizing. I always remember how hot it got, and that's even with the door shut. And then the door got opened after it cooled off, and you took your item out, and it was suddenly magically hard and glazy and shiny because of the heat that was applied. And it sintered, or it fired the clay and made it impermeable and vitreous, and now a cup that you can put your coffee in. And in a cement kiln, a very similar process happens. So we add our calcium carbonate, we add our silicon dioxide. They also add other minor elements to the mix, or the meal as they call it, but these are the big ones. Right? And it goes into a cement kiln. Now these kilns can be kind of complicated. I'm not going to pretend to know exactly how all the material flows work, but the ultimate end of the process is the rotary kiln. It's a long tubular structure that looks a lot like this right here. This is a cement plant in Canada, Lafarge in Nova Scotia, and they have 2 rotary kilns in the cement plant, and these look like big long pipes, right? These could be anywhere from, say 15 feet in diameter, 15, 20 feet in diameter, and hundreds of feet long, 300, 400 feet long, something like that. And this entire tube is heated. So you don't see it in the picture, but inside of there, this whole thing is lined with refractory, heat-resistant insulating material on the inside of that. All right? So it's a steel pipe lined with insulating, fire-resistant bricks or liner. And the cement materials, our calcium and our silicon, are fed into here, preheated. There's an entire structure above this kiln, housed in these buildings, that preheats all this stuff, drives off the water, drives off the carbon dioxide from the calcium carbonate. They call it a precalciner. So basically you're converting CaCO3 into CaO, which is quicklime. So that's lime, as in quicklime, reactive lime. CaO then enters this long rotary kiln, and it kind of tumbles through here. So this entire kiln rotates axially. So these tubes are actually spinning. and there's rollers. Looks like there's 1, 2, 3, 4 sets of rollers visible in this picture, and it probably even has another set in the back here. And those rollers rotate the kiln, so all the material is tumbled through this. And then at the very end, there is a tube that comes down the middle. All right, and that's your kiln main burner. And there's a gigantic flame that's emitted from the end of that burner. They usually inject coal, pulverized, powderized coal, into this main burner. The main burner flame then heats the kiln. What temperature do you think we use here? It's like the oven in your kitchen, right? You know, it's 350. We're going to bake it at about 350, 450 degrees. Cook our pizza, right? No. This kiln operates at 1450 degrees Celsius, which is about 2,650 degrees Fahrenheit. That's quite a bit hotter than the oven in your kitchen. It's even hotter than the kilns we used to fire our clay pots in art class. This is extremely freaking hot. That actually is within the range of the melting point of steel. Okay, steel, depending upon the alloy, melts between 2,500 and 2,800 degrees Fahrenheit. This kiln is operating in that temperature range. This is so hot, we could melt steel in here. Really, really, really hot. So that whole tube of this kiln is, like I said, lined with heat-resistant materials to, number one, keep the heat from melting the steel tube or burning through it, and also to keep the heat inside the kiln. We don't want a lot of heat escaping, because you can see there's a lot of surface area here exposed to the atmosphere. And even if the insulation is there, let's say they have a foot of insulation, a foot of refractory material lining the kiln, at 2,650 degrees Fahrenheit, over this large of a surface area, you're still going to have a lot of heat loss. So they got to fire enough coal into this kiln to run the process of creating cement, calcium silicate, and all its various formats, and also sintering the material and creating what's called clinker. So at the end of the kiln, so obviously we put in powder. These materials are in powder form. They're very finely ground up to give you the surface area for the chemical reactions. But as it tumbles through here, and it falls out this end right here into what's called a clinker cooler, the cement has formed little balls. So they're probably about 1 inch in diameter or so from what I've seen in the videos. The clinkers, they're little balls of gray stuff. Because as the material has gone through here and hit this temperature, it is actually fired sort of like the clay in this cup. And we have a ceramic kind of clinkery, kind of agglomerated mass of stuff. And it falls into a cooler, it cools them off using air, forced air. And then they go to a mill, a ball mill or something like that, and they grind the clinkers up into the powder, and then that powder is your cement. The cement then gets sold to people who make concrete, and then when you go to the store and you buy the bag of concrete or you order a truck of concrete, that cement is in there, and as soon as water touches that, the chemistry that happened inside this kiln at 2,650 degrees Fahrenheit goes backwards. And suddenly we go back to the natural state of these calcium silicates, which is rock. When you go outside and you dig in the ground and you get a chunk of rock, this is a very representative formula for what that rock could be made out of. And what comes out of a volcano as volcanic ash, a lot of it is this, because these are the most common kind of elements that are in the Earth's crust. And the volcano has achieved these temperatures, and it naturally created cement. So human beings over the past 2,000 years have learned, hey, wait a minute, we can do this ourselves. We don't need no stinking volcano. We can make our own volcano. And to make a volcano, you need a lot of energy. So to fire this main burner, now most cement kilns, traditionally most of the heat is supplied through this main burner. Pulverized coal is the normal classical fuel, but some kilns will burn natural gas. Some of them have used fuel oil. Some of them have used biomass in various amounts, wood chips, sawdust. You can really, really burn a lot of different things in this burner because of the high temperature and the long, 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 long furnace that you have. And then, in the field of combustion technology, this is called residence time. So we have a very high residence time for our chemistry to happen inside of a cement kiln. So we can burn a lot of different fuels and actually get them to fully combust. Okay, natural gas is very easy because it's just methane. It's easy to burn that. But sawdust is a little harder because it's a more complex substance. So you need a little bit bigger of a furnace to burn sawdust versus natural gas. The other things that go on here is obviously, from what I understand, typical cement kiln, I don't know if it's on a per kiln basis or a per plant basis. It's probably a per kiln basis. So that means each one of these rotary kilns, each line here, requires about 300 megawatts of thermal energy, thermal power input. So to maintain our 2,650 degrees oven temperature, we need 300 million watts of heat. 300 megawatts. Most of it's supplied through this burner here. A lot of kilns will also have burners up inside of the calcination towers, the pre-calciners. They will add heat there. The designs are quite variable. I obviously don't know all of them, but just based upon what I've seen is they can add heat in the tower to preheat the meal coming into the kiln, in addition to adding heat down here at the end. So we got to have some source that can provide us with our 300 megawatts of heat. So we got to have heat to run the chemical reactions. We have to be able to dissociate the limestone and blow off the carbon dioxide from the limestone. We have to be able to kind of break apart this silicon dioxide a little bit to get it to merge with calcium and get them to kind of come together. We got to drive off all the moisture. We got to get rid of all the water molecules that are embedded in all these minerals that are naturally coming out of the earth. And then we got to provide enough heat to get up to 2,650 degrees. And then we also got to provide enough heat to deal with the losses. So this whole kiln, heat is being radiated and convected from the surface out the outside of it. We also need to heat the air that we use to burn the fuel. So you're burning coal, and you got to provide enough oxygen to combust that. So you got to heat that atmosphere up before it goes in here. You got to get it to the right temperature. You got to maintain the heat loss that's going out the stack. So you're burning the fuel, you're creating all this exhaust gas. That gas is going out to the atmosphere. There's heat going with it, so you got to deal with that. You can capture some of it and reuse some of it, but not all of it. So at the end of the day, we need 300 megawatts of thermal energy, thermal power to run our cement manufacturing facility, just to heat it up. Where do we get 300 megawatts from? This is the $64,000 question, and it's a very indicative as to why the manufacturing of cement is responsible for so much greenhouse gas emissions. So you need energy. You're burning fuel to get that energy. You're burning coal or gas or oil or whatever to get your 300 megawatts. So some of the CO2 emissions come from burning the fuel to get our power that we need, our heat. Another fraction of the CO2 from cement plants comes from breaking down the limestone. So we have calcium carbonate. So this part of the calcium carbonate, that part of the limestone, that part is the carbonate that's been buried in the ground for millions of years. Millions and millions of years ago, organisms lived like shellfish and all these things that created the limestone. Limestone is a biological, for the most part, it's a biological material that came from shells of organisms that created, when you get a clam shell or a snail shell or a mollusk or something like that, that shell is made of calcium carbonate. And the animal gathered the calcium from the water that's dissolved in the water, and they gathered the carbon dioxide that was dissolved in the water, and they put them together because that reaction is thermodynamically favorable, and they started building their shell out of it. And over the millions and millions of years, those things died and they went to the bottom of the ocean. And as the world changed and the plates moved and land became sea and sea became land, limestone was deposited, and then people found it, and we use it to make cement and other things. And in the cement kiln, the heat dissociates this molecule and it creates calcium oxide, CaO, and carbon dioxide. So the carbon atom and two of the oxygens go to carbon dioxide, and the calcium and one of the oxygens goes to calcium oxide. This becomes part of the cement. This goes off to the atmosphere, and out of a typical cement kiln, something like 55% of the carbon dioxide coming out of the stack comes from this reaction. And then the other 45% comes from the burning of the fuel to get the heat that drives the process. So this part is intrinsic to the manufacturing of Portland cement. All right? This is part of the chemistry of making cement. 55% of the greenhouse gas emissions. So let's just do half and half. That means that 4% of the world's greenhouse gas emissions are coming from this chemical reaction that's going on inside the cement kilns. That's actually very significant, because I think that aviation, commercial aviation is responsible for 3 to 4% of global carbon dioxide emissions. So all of the airplane flights in the entire world is the same amount of CO2 as this chemical reaction inside these cement plants. And all the concrete that we make, and all the cement, 4%. The other 4% is just providing the heat to heat the kilns. It's pretty significant, right? You think, a typical person that's concerned about climate change might think that cement companies aren't doing their part in trying to reduce this. Oh, they're just greedy, they don't care, they're not trying to find alternatives. That is false. That is absolutely not true. So if you're a cement manufacturer and you need 300 megawatts of power, of thermal power to run your process, do you think they have to pay for that energy? Absolutely. So every industry, we tend to think that industry just wastes energy just because it wants to, and it's too lazy to make its processes more efficient. Well, that's not really the case. This energy costs money. 300 megawatts is a lot of money to spend. They're spending, a typical cement plant to create that amount of heat is spending a very, very large fraction of its revenue stream on making the heat to run the kilns. I don't know the economics offhand, but I would guess that this is the biggest expense in a cement factory, the fuel. It's probably more than labor, and probably more than the raw materials. This is a very, very large amount of money to spend to generate heat, to make 300 megawatts. So, what is the cement industry doing, and what have they done to deal with this issue? Okay, well, they can make the cement plants more efficient, all right, and that's happened. So cement plant has along the kiln, and the flame shoots into this end over here, and the building that's at the other end contains a whole lot of stuff. There's a bunch of things in there that I'm not going to sit here and pretend to be an expert on, but there's heat exchange that goes on in there. So that hot 2,000 degree air coming out of the end of that kiln goes in. Let's just make this the end of our kiln. Okay, you've got air, and the first thing going on is the materials that are going into the kiln are flowing counter current against the air. So you're using the exhaust heat to preheat the materials as they come through. And up above here, there's a bunch of cyclones and various ducts and various pieces of equipment that allow that material to be heated up by the counterflow of the exhaust gas. You also have a set of heat exchangers that preheats the air that's used to burn the fuel. So they will use the exhaust gas to preheat the combustion air to burn the fuel. That increases efficiency. They have various sets of pieces of equipment up here that allow incoming materials to flow counter against outgoing materials, either solids or gases, and heat is transferred from hot to cold. So the outgoing hot stuff preheats the incoming cold stuff. That's the absolute basic way you can make a cement kiln more efficient, is preheating the process. The other thing is taking advantage of the thermodynamic quality of the energy. So when the cement materials go into the kiln, go into the top, into the very, very beginning of the process, there's moisture and things in there. And the moisture boils off at a fairly low temperature, 212 Fahrenheit, 100 Celsius, gets rid of your bulk water that's in the incoming sand and limestone. There's also crystallized water, which probably comes off at a slightly higher temperature, but still pretty low, 300 degrees Fahrenheit, say 100, let's just say 100 Celsius, 212 Fahrenheit, then you get rid of the bulk moisture, and then you go, let's just say 200 Celsius, 400 Fahrenheit, gets rid of your crystallized water, okay, and then you go to 900 degrees Celsius or 1800 Fahrenheit, and now you're calcining and you're burning off the carbon dioxide from the limestone. And each of these steps is performed using kind of exhaust or lower grade heat from the kiln. And that enables you to better utilize the energy, because if you were to just dump the incoming raw materials into a 2,650 degree furnace, you would be doing a process that can happen at 100 degrees Celsius or 212 Fahrenheit, and you'd be putting it into an atmosphere that's 1450 or 2,600 degrees Fahrenheit. It's like using a baseball bat to swat a fly. It's far in excess of the force needed for the job, and it would be very wasteful of that very high grade, very high temperature heat to be just boiling off moisture. So they will make sure that these steps happen in succession, and then right here is probably right about the entry point to the rotary kiln, and then the cement meal goes from 900 degrees Celsius and it goes through the kiln, and at the very end it hits 1450 degrees Celsius or 2650 Fahrenheit. And you have now reached your main burner flame, and the energy can cascade all the way down to 100 degrees Celsius or 212 Fahrenheit before it goes out the exhaust stack to the atmosphere. So that's one way that's another way they can improve efficiency here. They call this taking advantage of energy quality, or exergy. So cement kilns do this. Obviously they've done this here. This has probably been happening since probably the 1950s, whenever these pre-calciner type of towers were installed on these things. Early, mid 20th century, people recognized that that was a good idea. So it's now 2022. What are we doing now? How are cement companies dealing with this? Okay. Now we've kind of taken advantage of the energy about as much as you can. It's really hard to really go any farther with that. So what about the fuel itself? So I said they burn coal. Coal is the traditional fuel. And why is coal a good fuel in a cement kiln? Well, coal, it's traditionally been cheap, although now natural gas is sometimes cheaper. But it also produces a really, really nice flame for running this process. So the coal is injected as a powder. So you have your kiln, and you've got the burner, which is just a pipe with a nozzle at the end of it. There's a nozzle that goes out the end. And they can blast this powder and air into this nozzle, and they can get a nice long flame. Really, really nice flame with a very high aspect ratio here for the length, and have this flame. And with coal having a lot of carbon in it, this flame becomes very luminous. It's very bright. And the energy that's released by the flame, a lot of it is released as radiant heat. And that radiant heat goes directly to the walls of the kiln. And it heats up the materials very efficiently. All right, because this is spinning, and the cement product is at the bottom here, and it's tumbling around. And you got this big, long flame that's radiating heat for probably dozens of feet into the kiln. I mean, these flames, from what I understand, are pretty long. And the advantage there is you're heating the material directly. With radiation, you're not heating the air going through the kiln. You want to heat the material, not so much the gas that's in here. Coal works really good for that. Natural gas gives you a very weak blue flame, and it doesn't have the radiant heat ability that coal does. So that's why they like coal. It's a good fuel for this. The other thing is coal, we tend to think of it as being a dirty fuel, but in this process, the dirt is not a liability for you, because this entire kiln is filled with powdery, cementy, mineral matter that's tumbling around. So a little bit of fly ash isn't a big deal. This is a very good application for coal as an energy source. So that's what they use. 45% of the greenhouse gas emissions from the process are coming from the fuel. But your guys at your cement kilns are like, well, this coal is really expensive. This is costing us a lot of money. What else can we burn as fuel? Okay. People are very, very innovative with this stuff. So, the cement industry recognized years and years and years ago, especially in the 1970s and 80s, that wait a minute, there is a social need to dispose of a lot of various materials. And the 1970s and 80s was right about the time when a certain piece of legislation went through United States Congress called RCRA, the Resource Conservation and Recovery Act. And RCRA basically was the thing that finally regulated waste on a national federal basis. So the United States government finally started to regulate waste products in a very enforceable and comprehensive form. Everything from garbage that you would throw in your trash can at your house to hazardous waste produced by industry. RCRA mandated, especially for hazardous waste, that if the waste could be treated, that it had to be treated and not disposed of in landfills. So we're talking about things like industrial solvents, oils, waste chemical products, things like that, that people were just dumping into surface landfills and contaminating all sorts of soil and groundwater. RCRA now said, no, you can't do that anymore. And suddenly there was a market for waste disposal of things that had a lot of heating value. So when I say heating value, I mean if you were to burn that waste material, it would give you a lot of energy. So think about like motor oil, paint solvent, industrial solvents, flammable chemicals, even things like tires, plastics. They all have a lot of intrinsic energy value to them if you were to incinerate or combust them. And RCRA sort of forced that on industry, saying, hey, you need to do something other than just burying this stuff in a hole in the ground. And the cement companies saw this as a major opportunity because this furnace, being how big it is a perfect environment for incineration. All right, so if instead of injecting coal into this flame, you were to inject waste, xylene or mineral spirits or acetone or motor oil, it would burn very, very well at 2,650 degrees Fahrenheit. Okay. One of the things that's in as part of RCRA is the standards for the treatment and disposal of hazardous waste. And part of one of the most common ways that hazardous wastes are managed is through incineration. So there are dedicated plants out there here in the United States and all around the world whose job it is a commercial incinerator for hazardous waste. So their job is just to take in hazardous waste, light it on fire, and make sure they properly deal with all the emissions. And in a regulation like RCRA, they enforce the destruction efficiency of those incinerators. They require them for burning various different wastes that they be at 99.99% destruction efficiency. All right? I think maybe even some of them operate at 99.9999%. That's a very, very high, it's what they call 4 nines destruction efficiency, or 6 nines destruction efficiency. These incinerators are doing this while they're operating at 1800 Fahrenheit or 1000 degrees Celsius. Okay, that's actually quite a bit cooler than the cement kiln, all right? And we're able to achieve very, very high destruction of things like really nasty stuff like PCBs, polychlorinated biphenyls, dioxins, okay? Chemicals that are very bad for human health. We're able to destroy them at very high temperatures really, really well. But the obvious downside of doing this in a dedicated hazardous waste incinerator facility is that you are basically burning fuel just to incinerate the waste. And cement companies realized very early on, wait a minute, we could incinerate the fuel incinerate the waste as a byproduct of making cement. And it seems like a really good synergism of industry. You guys get your stuff destroyed, we get heat, and we get to sell cement and reduce our coal usage. Right? It's a great idea, you'd think, So, the result is that a lot of these cement plants are fitted with systems that allow them to burn all sorts of industrial waste. So this plant in Canada and at Lafarge, they have a system where they burn tires. All right, if I can get this to play. So they burn tires as fuel. All right. So they're opening up a truck here. There's going to be some tires in there. There they go. And there's the tires. And here's the kilns. And I think that it's like 40 to 50% of all tires that are disposed of in North America are burned as fuel in cement kilns. So they got this complicated, crazy set of conveyors. And these tires go up through these conveyors. And, you know, they go on this nice path through various pieces of equipment, and ultimately tire goes down into the kiln, and it drops into the gates of hell, right, at 1450 degrees Fahrenheit or Celsius, or 2650 Fahrenheit. And that tire, obviously rubber, has a heating value similar to that of oil. So if that tire weighs 20 or 30 pounds, that's like 20 or 30 pounds of diesel fuel. And these cement kilns actually get paid to take the waste materials. They don't have to pay for their fuel. They get paid for it. All right. And now, obviously, somebody will say, well, a tire is primarily made from petroleum products, and you're still emitting greenhouse gas emissions. That's true. Okay? So if you're burning tires as fuel, you're still burning, it's like burning fuel oil. But the thing with it is where is that tire going to go if you don't burn it? What are we going to do with it? The market for recycled tires isn't big enough to handle all of the tires that we throw away as a society. We throw away more tires than what the recycling market can currently manage, so the rest of them either got to go to a landfill or they go to cement kilns where they use them as fuel. So that's the kind of the story. A lot of industrial waste from all sorts of manufacturing processes is sent to cement kilns and is burned off as a fuel in the kilns. And that reduces the amount of coal that they have to use. So most of those alternative fuels are ultimately derived from fossil fuels. So it doesn't very well reduce greenhouse gas emissions when you consider it in and of itself, but it is providing a service that is definitely needed. If we were to instead send the solvent waste, the industrial solvent waste, to a dedicated hazardous waste incinerator, then we would be creating the CO2 emissions from burning the solvent itself, burning the fuel to keep the incinerator hot, and also the cement plant would then have to buy that much more coal to heat its kilns. So if you think of it that way, you actually are reducing greenhouse gas emissions by burning petroleum-based waste products. So that's how it's helpful. It saves the cement manufacturers money. It reduces the possibility of waste contaminating the soil, and it does ultimately reduce greenhouse gas emissions if you were to instead just burn the solvent for the sake of getting rid of it and then have to use traditional fuel to make cement. Most of these cement kilns only can supply, say, 50% of their heat from things like tires, because the tires and the solvents and stuff all have contamination in them that can cause the quality of the cement to be not ideal. So a tire obviously has steel wires in it. So your typical tire has the belting that's in the tire, the reinforcing steel. When they drop the tire into the cement kiln, that steel actually oxidizes. It burns. This 2,650 degrees Fahrenheit is hot enough in an oxidizing environment. This atmosphere is not only is it this hot, but it has excess oxygen. And that temperature with oxygen is enough to get the iron in the steel to combust. And that iron actually provides energy to the kiln because it's combusting and it's creating iron oxide, okay? And then the iron oxide is actually one of the minor ingredients of cement. So the cement companies then don't have to add as much iron oxide to their cement mix because the tires are providing a portion of it. As long as you know how many tires you're burning, you know how much iron approximately is how going into the process, and then all of that ends up in the cement. So if they burn fuel or they burn waste in a cement kiln, all of the ash that's produced by that waste becomes part of the cement. So if you were to burn household trash in a cement kiln, which there are places in the world that do that, all the ashes from the garbage would become part of the cement. So they have to be careful how much they use, otherwise the cement quality could get off because of the ash that's contaminating the cement. But the people who run these kilns do a very good job of making sure they do a good mass balance and know exactly what they're burning so that the quality of the cement isn't negatively impacted. So that's it. It's complex stuff, but globally, manufacturing of cement is 8% of all of our CO2 emissions, which is double that of aviation. So, you know, the popular press likes to say that flying is such a big source of greenhouse gases. I mean, it is. It's about 3 to 4%. But in the grand scheme of things, making cement for concrete makes twice that in greenhouse gas emissions. Maybe someday in the future we'll be able to achieve these temperatures using electricity instead of burning fuel. So if we could electrically fire the cement kilns and achieve this temperature without fuel, that eliminates at least 40 to 50% of the CO2. And then the other side of it, the other half of the emissions, you may be able to capture that carbon dioxide gas. If you were to use electricity, then you can make the entire cement kiln a closed process. You don't have to have atmosphere coming in and leaving and an exhaust gas. You could close the entire process in a loop and capture the carbon dioxide that's emitted by breaking down the limestone and possibly sequester that CO2. And that would be as much as 4% of global CO2 emissions if you did it for every cement plant. And then you get your 300 megawatts of thermal energy from electricity. So that's something that may happen someday, and we'll see. The other idea is to go back to cements that aren't as energy intensive. Instead of using Portland cement that has to be fired at 2,650 degrees, you could use lime. Lime only needs to be fired at, say, 1,800 Fahrenheit or 900 Celsius. And the lower temperature results in less energy usage. So you could cut your emissions from the fuel side of things by using a lime-based cement for various applications. So you go from, instead of 45% coming from the fuel, maybe only 25% would come from the fuel or something like that. So that's cement, a very basic material and a very sort of hidden from view, not so popular really to talk about and get excited about versus other emitters of greenhouse gases, but it's definitely important because when you have one industry that's with this very, very basic process that's responsible for almost 1/10 of the greenhouse gas emissions, that's a big deal. So that's the story of Portland cement.